welcome. Thank you for coming to my talk. As Claudia already introduced, Lennart Oldenburg, master student, computer science, Technische Universität Berlin. This is my thesis work on addressing unavailability issues in anonymous communication systems. And because it's my thesis work, there's some bits and pieces that are ongoing work, just so that you know. But let's start right into it. Why does anonymous communication matter? First of all, what do we mean by it? For my thesis, I consider it for individuals to gather and share information free from surveillance. So you can communicate without anyone knowing what you communicate and also with whom and when. And this is usually something that we would like to have for anyone available as a technical tool, readily to use, but especially critical for certain kinds of groups that are under a lot of pressure. For example, whistleblowers, dissidents, journalists, lawyers, and even, for example, artists to express themselves freely. So for them, it's especially critical because they might depend with their life on having these tools available. When we talk about securing communications over digital infrastructure, usually two vectors are relevant. First of all, obviously the content. We want to keep the content confidential. But often overlooked is the problem of metadata. That is what I mentioned earlier with who is talking to whom, for how long, with what kind of frequency, these elements of data. And it is important to keep the content confidential, but we should not overlook the other data that is produced while communicating. And especially in the recent years, we have seen quite a bit of uptick in cryptography, especially since the Snowden revelations. Lots of organizations started integrating end-to-end encryption into their products. And something that you can use to communicate securely using end-to-end encryption is readily available nowadays to the masses. If you use Signal or WhatsApp, we at least believe that they use end-to-end encryption, although we might not be able to verify it. But regarding protecting metadata, strong anonymity systems are still kind of missing in practice. So we have Tor, but technically it's not a strong anonymity system. And this is due to a number of reasons. Two of them I'm trying to improve in my work. First of all, it's about trust. And second of all, the title, it's about unavailability in these systems. So what do I mean by trust? Ideally, we would like to be able to communicate over digital infrastructure without having to trust the infrastructure itself at all. It would be nice if the infrastructure could be controlled by one adversary, which is strong and controls everything and sees everything, and still be able to achieve confidential and anonymous communication. And amazingly, there is a system that achieves this guarantee. In this case, I picked computational private information retrieval, which is introduced already in 1997 by Kushila and Ostrovsky. And on a high level, this is how computational private information retrieval works. We see here client A communicating with server S maintaining the database of data in the system. The client has two functions, query and decode, and the server executes one answer. And the client is now interested in one of the indexes in this database, but it does not want to tell the server which one it is retrieving. So it uses the query function and hides the index of interest, in this case index 4, and usually needs to take into account how large the database is. And this query is computed and sent to the server, and the server then executes the answer function on this query. And it is crucial that the server executes computational cryptographic computations over all entries in the database to hide which one was actually retrieved. And based on the result, it computes the answer and sends it back to the client, which is then able to use the decode function to retrieve the actual element. In this case, maybe a message hello at index 4. Right. So this is, from the trust perspective, this is amazing, but this comes at certain costs. Chiefly among them is that the server computational load is quite high because of all the cryptographic functions that we have to compute. And also the overhead in terms of what the client needs to put onto the link layer, so like in terms of network overhead, is also significant. So what can we do if we look for a more balanced distribution of load? We can maybe allow a little bit more trust into the system. So if we're not trusting none of the servers, we might be trusting one to remain honest at all times, which is exactly what any trust captures. And there's a number of ACS that work under this trust assumption, but the most well-known one is probably the mixnet architecture, which was introduced by David Chaum in 1981. Again, on a high level, this is how a mixnet can work, or used to work maybe. We see 3 clients, ABC, and 3 mix servers, 1, 2, 3. And any client that wants to communicate onion encrypts its message through the cascade of mixes, 1, 2, 3, and sends it to the entry mix. The entry mixes and the other mixes usually work the same. They collect messages based on their mixing strategy. They decrypt their layer of encryption. They cryptographically shuffle the set of messages locally, and then they forward the batch to the next mix, or if they have the last mix, to the recipients. And it is especially the step of shuffling, cryptographically shuffling the set of messages, that unlinks incoming from outgoing messages. And so if we trust one server in this chain to remain honest at all times, no adversary observing everything will be able to tell which incoming message is which outgoing message. This is how we achieve the unlinkability. And obviously this comes at the price of latency. So we have to configure these mixes using to have a mixing strategy. And this usually involves delaying messages for quite a significant amount of time. But what, for my thesis, I like better is the more balanced compute demand on server side, and also the, compared to CPIR, less good put overhead. So we have to put less onto the wire to achieve our anonymity according to any trust. Okay, that was the issue of trust. So now let's focus on the issue of unavailability. And my pitch here, the idea that I want to get across, is that strong anonymity mixnet, at least, are Byzantine distributed systems. And we know quite a bit about them. They are like a large number of nodes, usually in any modern case globally distributed. They have to work together to achieve their common functionality over a best effort network. That might involve difficulties. And also some nodes of this system might deviate from protocol. That's when we call them Byzantine. And this can include adversarial action. And it has been long established in Byzantine distributed systems that they suffer certain faults. For example, processes might fail or are super slow to respond, which is something that we cannot detect over an asynchronous network. We don't know if they actually failed or if they're just super slow. We can see messages getting lost on the way, or also being delayed for amount of time that is not usable with our protocol anymore. We have to time out and start over again. We can see network links breaking. Admittedly, that was probably a bigger problem in earlier internet days, not so much today anymore. But for example, consider a client connected to the service via a cellular connection, and the cellular connection experiences troubles. That could also be a network link breaking. And then all of these faults might happen randomly or like by themselves, but also caused because an adversary might tell this node to not send a message or to crash, for example. So all of these things can go wrong. And when you review current, like contemporary mixnets at least, and also other ACS, they acknowledge these problems, they are aware, but not really always address them and don't really plan for things failing. And my idea behind this is that if you don't handle these failures, they allow a denial of service on the users, in the sense that an adversary who's able to control the network with these failures might simply shut the service down for a user so that they are not able to send a message across anymore. And think about a mixnet where one of the mix servers crashes, the whole cascade has to stop and is not able to route messages anymore. And if this problem is not fixed in some kind of timely manner, users will inevitably going to divert to other communication means because they need to communicate, and that those might be less anonymous, less secure, and then the adversary would have achieved their goal. So what can we do about it? We propose to structure the ACS architecture mainly around the fault tolerance principles, so like integrate redundancy and fault tolerance deeply into system architecture. We build upon the mixnet approach that I introduced earlier. Specifically, we propose to use timed pool mixes arranged in multiple independent cascades. Obviously, we require clients to communicate with constant bandwidth. So in contrast to the picture that I showed earlier, all clients have to communicate all the time. If they're not sending a genuine message, they have to send cover traffic. And also, we introduce cover traffic on side of the mixes. So mixes have to add garbage messages in the, so to say, to the list of messages they currently handle to, hide clients. We have to assume a little more trust than the original mixnet. We have to assume that one honest server is present in all the cascades that we're integrating into the system at all times. That is something that we cannot get around because this is how mixnets achieve their anonymity guarantees. Our goal is to hide sender-recipient relationships of genuine conversations to a third party. So we assume that senders and recipients know each other, but a third party should not know who is talking to whom, when, for how long, right? And in terms of an adversary, we assume that this is a global passive adversary, GPA, and this adversary can also become active anywhere except for the one honest mix per cascade. And depending on what kind of property you're looking at, it also does not make sense to compromise all clients, but in general, this would be possible except for the two conversing clients. Okay, so what can we do along these two axes that I mentioned, trust and resilience? First of all, let's consider trust. My proposal here is to limit the window of compromise that an adversary might have into uncovering sender-recipient relationships in case he or she is able to compromise an entire cascade. And we do this by frequently reassigning the mix duties. So usually you talk about a mixnet with a static configuration of mixes, and my proposal here is to rotate these mixes frequently among a large set of candidate mixes, which is exactly where our search for more balanced server requirements comes back into play, because more entities might be enticed to provide mixed functionalities. As intuition, maybe I think of it as a self-healing property. Maybe if you work in cryptography, you might know post-compromise security in crypto systems. This is exactly the kind of characteristic or property that allows to regain secrecy of a test session after the adversary has compromised some amount of state. And I think of it like limiting the window of compromise by having this frequent rotation put into the protocol regularly that should increase limit the risk. For this, we definitely need an unbiasable public randomness source to elect the mixes in a way that is not biasable by any kind of large adversary. And luckily, cryptography has made progress in this area, mainly in the area of distributed ledger technologies. Bone et al. In 2018 introduced verifiable delay functions, and they're pretty amazing techniques, also far more complex than I'm abstracting here. I simply see them as a function that you put in public data, so it is known to everyone. And the computation of this function always takes t time steps, no matter the amount of compute cores that you put in, whether you're computing it on 1 core or 1,000, and you will end up with an unbiased shared output that you can use for some computation. And I'm showing this in a figure in a minute. But let's talk about availability, the second axis. The idea here is to prevent the denial of service that I mentioned earlier by, facing the faults that can happen. And the key here, which sounds kind of nice, is redundancy in space and time has to be integrated into the system. So you have to provide more resources in order to be able to handle some of them failing. And regarding the root causes that I mentioned earlier, we can address them with individual techniques, quite known from fault tolerance. So for slow and fail processes, we propose to introduce the multiple independent cascades. We call it cascades matrix, but it doesn't really matter. They are independent, they work in parallel, so they can handle failures of faults of them. Regarding delayed or lost messages, we instruct clients to send each genuine message to all cascades in parallel and also in the subsequent round. So we can tolerate loss in this round of all of them, at least as long as one of them is going through in the next round, we can still make this transmission. And finally, this is an idea. It did not really work out in our implementation. This is why I'm only proposing it, is to use forward error correction on the network layer to mitigate message corruption. So if you send a bit more data in a round, the receiving node might be able to correct corruptions without having to retransmit it. So coming to a system layout, a figure, we see this figure has 3 parts. The first 2 parts are concerning establishing the cascades matrix that everyone shares, like sharing the view of the server nodes. And the third one is about regular round operation. So let's start with the first 2. We see here that there's a PKI process, which is also something that we assume to have available for nodes to exchange public key material. This PKI process accepts registrations by any node in the system, either as a client or as a mix. They register their intent, so to say. So I want to become a mix node in the next round, for example. The PKI collects the public key material for a certain amount of time, and after which it publishes the public keys of all nodes that registered as mix intent to all nodes, which then, in part 2 of the figure, can compute the hash of this list of public keys and use this hash as input to the VDF, the verifiable delay function that I mentioned earlier. This step will take the team time steps, which is exactly where we achieve our unbiasable randomness, because no matter how big the node, if it's actually a server node or if it's like a smartphone, they will require the T time step to compute the output. And this output is a seed. This seed we use to seed a pseudo-random number generator, from which then all nodes locally and individually can compute the mixes of the cascades. And once this is done, we can move into regular round operation. You see the same mixes located over here. Some of them might be adversarial, displayed in red. Some of them might be honest, in green. And now clients who who want to communicate via this infrastructure, they again onion encrypt their messages. If it's a genuine one, in this case, they also put it into the queue for the next round. But if they're idling, they are required to send cover traffic, and then they don't send it again in the next round. Once their messages are delivered to all entry mixes individually, these mixes do their job. In case they're honest, then they unlink incoming from outgoing messages and add cover traffic. But if they're adversarial, they might simply pass the messages on in the order they received them. But the point in this operation here is that you can see no matter if a whole cascade fails, or even if all messages from the exit mix to the clients are lost on the way, as long as we have one way to get through to the clients, we will. And if it does not happen in this round, it might happen in the next round. So this is quite a bit of overhead. Like, this is a lot of resources just to achieve resilience. So we definitely need measurements to find out if it's actually worth it, to see if our resilience works. The goal is to have some real-world measurements. Usually a lot of these resource arguments are made on simulations or based on simulations. We wanted to try to actually obtain real-world data. So we developed a public cloud ACS testbed. Currently it's on the Google Cloud. It runs across 17 regions on 4 continents of this planet, and spawns machines for each of the node in the setup. We are interested in 3 measures: bandwidth usage to see what the goodput overhead is, load on the individual nodes, so CPU and memory usage. I'm not going to show the figure today, but this is relevant to see if it's actually viable to have a large number of mixed candidates. And third, end-to-end message latencies that should hopefully show if our resilience approaches are working, because we would like to see the same graph no matter the faults we introduce. We test these, or we collect these metrics under 4 different scenarios of faults. First of all, no faults, so like the happy case. Second, we put heavy network latency and loss on 3 regions out of the 17 for all the clients in this region, so only the clients. It's like 400 milliseconds latency, so like think of it as like a network link breaking down and all the packets have to be rerouted. The third scenario is about killing mixed processes. So what happens if during the irregular operation we kill two of the 3 cascades? Will the system be able to keep up with it? And fourth of all, the worst case scenario, combining the network partition and the mixed failures. To test this, we implemented the proposal that I presented earlier. We named it Zeno. It's written in Go, and hopefully we'll be able to release the source code when I passed my thesis. We had to take some simplifying steps because mixnets usually are quite complex software. So because the VDF topic is a very active cryptographic research topic, there's no library available that you can use. So we had to replace this by a script dummy call, which is instructed to run for a long enough time. And the process that collects these public keys is kind of outside the scope of our work. So this is like a fake process who just collects it and sends out the public key material. We compare it to a CPIR system. In this case, it's Pang, and this is an amazing system. They made a lot of progress. It was introduced by Angel and Sethi in 2016. We would obviously have liked to compare it to a mixnet architecture. In this case, I wanted to compare it with Vuvuzela, introduced in 2015 by Van den Hoff et al. But this was where my thesis time ran out, and I had to make a decision, and Pang was running, Vuvuzela was not, so I had to go with it. All the figures that I'm about to show, we instructed Zeno to be running across 3 cascades, each of them having featured like 7 mixes in all 4 failure scenarios. Pang, because it is a single server setup, it doesn't really make sense to crash this one server to see what happens. So where the mixed server failure setup scenarios are taken out of the question. And also the introduction of the partitioning latency kind of had a lot of difficulties, so we're restricted to the happy case here. We will still see the impact on the server side. Any figure that I'm showing is measured over 25 consecutive messages through the system, over 3 runs for 500 and 1,000 clients, user bases, and per scenario. So let's take a look at bandwidth on client side. We see here the 2 setups, 500 clients user base, 1,000 clients user base. Y-axis is the bandwidth usage, it's a log scale. And the 4 Zeno scenarios you can see in gold with a different pattern from left, no failure, to right, the worst case scenario. Blue is for Pang. And immediately we see that Pang uses quite a bit more bandwidth to get through these 25 messages without any kind of fault tolerance. So there's no redundancy here. And we see that even including lots of measures of redundancy, Zeno will be about a magnitude, order of magnitude less in bandwidth. Also, it is interesting to observe the patterns among the Zeno scenarios. So we see that adding network latency will increase the bandwidth that you have to put into place in order to get the messages through. That is nice to see. And also the 2 last scenarios are where we killed mixed nodes, like crashed the processes. So we see that less mixes result in less traffic received by the clients. It's also good to see this. Takeaway here is that client-side bandwidth usage is considerably less than in a CPIR system. Let's consider servers. Again, this is pretty much the same setup, except that the y-axis is not log scale anymore, it's linear. And because we have to consider, we have to compare like system level bandwidth usage, I aggregated the server individual measurements. So any bar for Zeno is for all 21 mixes. And the Pang system is just the one server, right? We see again that the Pang setup is quite more intense in terms of bandwidth usage. Also, the scaling from 500 to 1,000 clients is more than factor 2, as you might expect it. It's more like factor 3. And Zeno is pretty much scaling by factor 2 from 500 clients to 1,000 clients. That is nice to see. Also, the patterns persist, so adding network latency requires more overall bandwidth. Reducing the number of mixed servers ends up in less network bandwidth. I've drawn the average server requirement in terms of bandwidth as the red dashed line, just to convey the impression that as low as 70 megabytes up to 300 megabytes is not that much in terms of bandwidth compared to, in this case, the CPIR system. All right, and then hopefully the graphic or the figure that will show that our resilience efforts were successful. We see end-to-end message latencies in the cumulative distribution plot. On the x-axis we have the transmission latency, on the y-axis the fraction of transmitted messages. These lines are ordered by their latency value. So we have the 2 Pang lines in the beginning. They provide significantly less latency than our mixnet system, which was kind of to be expected because we have a lower bound on latency through the number of cascades. Still, it's good to see that this is actually shown in the plot. Again, the scale up from at any percentile here, above 50, from 500 to 1,000 clients is more than factor 2. I will need to increase the number of clients to test here, but I think this is an interesting trend to see that the latency grows more than by the factor you scale the clients. And also there's like struggles on the way to transmit all messages once you scale from 500 to 1,000 clients. But let's take a look at the Zeno measurements. We see that they are all quite closely grouped together. 3 of them a bit lower in latency than the rest of the 5, of which also the first 2 are a surprise, to me at least. The green and the red line, I hope you can see it. Those are Zeno setups where we already introduced network troubles. So those are not the failure-free scenarios, but already seeing latency. And I'm still investigating exactly why that is. I would have expected them to be like a little shifted to the higher latencies, but they're still in front. But the main message here is that no matter the faults we introduce, the figure pretty much, or the line pretty much proceeds in the way that we expected it from the failure-free case. So like no long tail that is like significantly deviating from the failure-free scenario, which means no matter if we kill mixes or if we introduce significant latency, the messages proceed according to the curve that we would expect them to proceed, or hope them proceed in the good case, which is precisely what we try to achieve, although there's like this question of ordering among them. Right, and the 500 clients were those produced 37,500 messages. The 1,000 client setups, obviously 75,000. So these are the messages that are displayed on the curve. Okay, coming to some conclusions. The point that I tried to make, or I'm trying to make with this thesis, is that unavailability is a serious attack vector in ACS. It can enable a denial of service attack on users that then have to divert to less secure means of communication. And maybe a bit the point about this is that the current ACS all acknowledge this situation but don't really tackle it. So there's kind of set in the happy Byzantine case. We assume that there's an adversary that is reasonably strong, but we still assume that no processes crash, no messages get lost, which is not the reality in distributed systems. Our proposal towards this is that we have to trade significant amount of resources to achieve resilience. So we could be more efficient in terms of network goodput if we diverted the resources that we used to achieve resilience towards routing messages. But this is a trade-off that you always have to make, scaling up or also achieving resilience. You have to put in more resources. Our proposal combines different fields, tries to combine different fields, for example, the ACS field, but also ideas from distributed ledger technologies and from distributed systems. And we consider the initial measurements with our planet-scale ACS testbed quite promising. Definitely, there's future work left. I have so many questions still to answer. I would definitely like to scale up the number of clients measured through the system. I would like to measure more scenarios. For example, in Pang, we definitely need the latency scenarios. Obviously, I would like to compare to a mixnet, actually, to see if our architecture is better performing in terms of latency than a not instructed mixnet. Probably this is going to be Vuvuzela because the source code is available. And then looking beyond just the system, the setting that I presented here, you could ask, how can we achieve group conversation in anonymous communication systems? How can we introduce asynchronous message retrieval so that clients don't need to be online in the round that they are supposed to receive the message and still be able to retrieve it without having to retransmit it? Or might a topology change be advantageous to us because we have a fixed cascades, we're assuming fixed cascades. There's lots of discussion around free route networks. Would that be beneficial to us? So there's abundant future work available. And with that, you can check my references also afterwards if you like. And thank you, that was it. Happy to take your questions.